Hello, here we're going to look at solving exponential equations and inequalities for level 3. So later on in this chapter, we're going to learn a method to solve where x is in the exponent. And it's going to be different than this, but this is a method that you can use with by hand methods. The method later will require calculators, but it will allow us to solve more complicated scenarios. All the ones that we solve today are going to be either whole number or fraction solutions. And so what we've got here is it's first going to start us off with rules of exponents. And the rules of exponents from earlier chapters are same base, add the exponents, power to a power, you multiply, and if you're doing same base divided by same base, the exponents subtract. This is an important rule here. This is what's going to hinge this whole page, to where if we have a base on both sides of the equations, and it says that if b is a positive number other than 1, so it's a little stipulation because there are some numbers that would make this not true, but if b is a positive number other than 1, if both of the bases are the same, their exponents must also be the same. And this should make sense, because if I said 2 to the third power, and I said it's equal to 2, the only thing that this exponent could be to make it equal is another 3. So essentially we say if your bases are equal, we can focus in on the exponents only and set them equal. So that's what we're going to need to use to solve this. Now, we'll also navigate situations like this to where we'll see things where the bases are not equal. Right now, 4 and 2 are obviously not the same base. We're going to use mainly this rule, a power to a power, you multiply rule, to help fix that. And we'll do it by putting things back into the same base. So for example, on this one, there's actually two ways we could have done it. They chose to re-express 4 as a 2. And in order to re-express 4 as a 2, we would need to call it 2 squared. 2 squared is 4. And then here's what we'll do. Here's what they did. They said, okay, my base here is 2. My base here is 2. Since my bases are now equal, I'm going to set these exponents equal. And so that's where they got the 2 times x minus 1 and the x plus 5. And then they just went on and solved a, regular old equation. And they got the answer to x is equal to 7. And as always, you can go back through and double check this. If I go back to the original equation and do 4 to the x minus 1 and set it equal to 2 to the x plus 5, you'll see here that we get 4 to the 6th power, and then here we'll get 2 to the 12th power. And if you type this in on a calculator, these two answers would give you the exact same thing. 4 to the 6th and 2 to the 12th are the same thing. And if you wanted to see that reasoning by hand, we could do that same trick as up above and realize that 4 can be the same thing as 2 squared. There's the 6. And then when you multiply those, you get 2 to the 12th is equal to 2 to the 12th. All right. So that's what we'll be doing. Now, some of them will be easier than others. This very first example, recognize that the bases are already equal. So that means we can jump right ahead to this. If the bases are equal, you can set your exponents equal. So then I could subtract an x from both sides, add a 1 to both sides, and get that x is equal to 3. And there'll also be various problems where your bases are not equal. And I'm actually going to do this problem 2 different ways to show you that whichever way kind of makes more sense to you, you would be welcome to do that. So I'm going to write the same thing twice. Method 1. is going to be to take the larger number and express it as the same base as the other side. To where I could call 4 2 squared. Right, so right here, 4 is the same thing as 2 squared. Now, when I do that, I have the same base, because it's 2 and 2, so now I can set my exponents equal. So when I do that, I'll get 3x is equal to a 2 times x plus 2. So we have 3x is equal to 2x plus 4. Subtract 2x from both sides, and we'll get that x is equal to 4. And you can double check this with calculators and go make sure that, and if you don't believe it, you can plug in 4 back into both those original equations and it will work. Now, other things that you can do. If you want to, instead of changing the 4, you can also bump up the 2. And what you'd have to do is recognize you have to square both sides. And when we do that here, you could apply this 2 to there to get the 4. And you get 4 to the 3x. Here is equal to, and this 2 would distribute to both, 4 to the 2x plus 4. And then you see you have same base, same base. You could set your exponents equal. And this right here, the 3x is equal to the 2x plus 4 is the same thing as the 3x is equal to the 2x plus 4. I will say people don't choose this method as much because it gets a little confusing to them because they have to now do something on both sides. Compared to on this method, all they had to do is simply re-express the 4. So most people do it like this, to where they look at the larger number and try to re-express it smaller. Now, there are a lot of different scenarios that can happen on this. Negative exponents will come into play. And remember the way that negative exponents work? Is that if you have an x to the negative power, it actually just tells you to take the reciprocal. So what you could do on this is think about how you could re-express it. The 9's the larger term, so that's the one I'm going to want to re-express. And 1/9, 9 is 3 squared, but in the denominator, which means if I wanted to get it back to the numerator, it will need to become negative. 3 to the negative 2 power is 1/9, because 3 to the negative 2 power is 1 over 3 squared, which is 1 over 9. So be on the lookout for situations like that, because sometimes you will see them as fractions. But now that we have same base and same base, we set our exponents equal. And when I add 1 to both sides and divide by 2, I'll get that x is equal to a negative 1/2. And I can show a double check on this one. If I plug in x as negative 1/2, we'll see that it does in fact come into 1/9. This 2 and this 2 would cancel out, so I'd have negative 1 minus 1. That's 3 to the negative 2, which is 1/9 is equal to 1/9. So these answers do check out. They are valid. Before we look at the next problem here, I encourage you to, if you're confused at all, rewind and rewatch the portion of the video where we just did some solving. That will assist you in understanding those steps, and it's pretty much brand new here for us, the steps that we took today. So rewatch 1, 2, and 3 if you're a little confused, because we're going to continue to build on to what we just saw. And that's going to be examples like this, to where my bases are a little more tricky to match up. I've got a 4 and an 8. I can't shrink down 8 to a power of 4, right? Because 4 squared is already 16. So sometimes what you're going to need to do is change them both and think about, is there a way I could re-express 4 and re-express 8 as the same power? And what that power would be is 2. 4 is 2 squared. 8 is 2 cubed. So be on the lookout, because sometimes you'll have to do a double change. And you know you have to do a double change when you can't re-express the 8 to become the base of the other one. Like there is no 4 to an even number exponent to give us 8. There is a way to do it as a fraction, and maybe you know how to do that from some of our past sections. That'd be a little tricky. But the easiest way is to re-express them both into the same base, and then set your exponents equal, which is 2 times an x plus 1 is equal to 3 times a 2x plus 3. So we'll get 2x plus 2 is equal to 6x plus 9. I'll subtract 2x from both sides. I'll subtract a 9 from both sides. And then when I divide by 4, we'll get that x is equal to negative 7 over 4. That problem was a little trickier because of the way we had to start it out, where we had to change both bases. Let's go ahead and look at number 7, which is another scenario where that will happen. You might recognize 9 and 27 are both powers of 3. And that's really the visualization step you'll need on that, is to recognize that that is indeed the case. And then we'll set our exponents equal. Alright, so we'll get a 2x plus 2 is equal to a 3x plus 12. Subtract 2x from both sides. Subtract 12 from both sides. And we'll get that x is equal to a negative 10. Alright. Visualizing things from the same powers can be a little bit tricky, especially when there's fractions. On this one, what you'd have to recognize is that I've got an 8 and a 16. Both of these are powers of 2. So I would have 2 cubed to get 8. And then 16, 1 over 6, well, 16 is 2 to the 4th. But since it's in the denominator, this is really 2 to the negative 4th. And then you can set those exponents equal. We get here after we add 2 to both sides. X is equal to negative 2 over 3. So I encourage you now to pause the video and attempt the remaining 3. See if you can re-express them as the same base, and then set those exponents equal. When you push play, it'll reveal the answers and steps. So go ahead and pause and try. Or if you're confused, re-watch. Alright, so 6 and 8 were both pretty standard. 6, the base was 5. On 8, the base was 6. On number 9, you actually could have done it 2 different ways. I chose to use base 4 and do 4 to the negative 3rd for 1 over 64. 4 squared for the 16. You also could have done it as powers of 2, though, and you would have gotten the same answer. So you could have decided to do it with 2 to the negative 6th power, because that's 1 over 64. And then 16 is 2 to the 4th power. And if you did it like that, you'd see that you'd end up getting the same answer. We get negative 6x plus 12 is equal to 12x plus 4. And if I went ahead, just for consistency's sake, if I now divided both sides by 2, which I wouldn't really do as my next step, I'm only doing it to show you that when I do it, why you get the same answer, because now this line and this line are the exact same. And sometimes that'll be the case, especially with powers of 4. Anytime you're using base 4, you also could have used base 2, but using base 4 will keep your numbers a little bit smaller. So, that's how to solve exponential equations of that particular type. We'll learn another way later in the chapter, but this is the way we will roll for now. I'm going to change topics now, but if you are still having any type of confusion, rewind and rewatch. The next section. This really could have been in 6.1, but as you saw from the length of those videos, that was long enough as is. It wants us to write an exponential function for the graph that passes through the two given points. Now, whenever we're doing these, we are assuming that we're talking about y equals a times b to the x. We're not going to have any h values or any k values. That's the assumption that we're making. And the reason that's going to be beneficial to us is that they're going to give us the y-intercept on every single one, and that y-intercept is going to represent our a value. So for example, you could go through on every single one of those, and whatever the number was with the 0, that's going to be our a value, because it's the value that we start with. And that happens anytime we have a 0, a, and we're not working with h and k values, which will be most of the time. You won't interact with those as much on this type of function because it messes all sorts of patterns up. So we're going to work with y equals a times b to the x. Now the only question is, how do I find b? Well, in order to find b, what you're going to do is you're going to take one number and divide it by the other. Now, you'll notice that all of these start with 0 and then move to a positive number, right? Like 0 to a positive number, 0 to a positive number. That means we won't have to worry about any backwards scenarios. We're moving forwards on all of these, which means all we're going to have to do is figure out, for that b value, what we are multiplying by over and over again to get this 4 to become a 36. Now, it's not as simple as 36 divided by 4, because that would tell us 9, because it actually went from 0 to a 2. So it's really asking, if I multiply by 4 by a number, I'll get something. If I multiply by that same number again, I'll get 36. Which might have you wondering, well, how can I figure that out then? What type of formula maybe should I use to find what that is? To find it, we're going to have to use a little basic math. And here's what we'll have to do. We're going to use this 2 as an x-coordinate, and this y as a 36. So it'll be y is equal to 36. We know our a value is 4. We don't know b, but we know that the x is 2. Because my original function is y is equal to 4, which was our starting value, times my b value raised up to the x. So if we substitute this x here and this y here, we can set this up as a solvable equation. And what we would do now is we would divide both sides by 4, and we'd get that 9 is equal to b squared. And when we square root both sides, we're going to get that b is equal to 3. Now, some of you guys might be recognizing, Mr. Cotto, what about your plus minus? We just took a square root in an equation context. Well, recall that for exponential functions, your b value either had to be greater than 1 or in between 0 and 1, so negative numbers weren't allowed. So that means that this one is 3. So there's the final equation. And the reason this works, and you can check it with either coordinate point, if I check it for this coordinate point, if I plug in 2 for x, 3 squared is 9, 9 times 4 is 36. If I plug in 0 for x, 3 to the 0 is 1, 1 times 1 is 4. So for all these different ones, you're going to have to use that similar pattern. So like on this one, to find the equation, I'll substitute in 486 as my y. I'm going to substitute in 5 as my x, and we're solving for b. which means on this one I'll divide both sides by 2 to get 243 is equal to b to the 5th. Now we're going to need to take the 5th root, or raise both sides to the 1/5 power, because remember that the 5th root is the same thing as something to the 1/5 power. And when you do 243 to the 1/5 power, you'll get that b value is equal to 3. So there is the original equation. So these will all be fairly similar as you're going through this process. So let's try a couple more. We'll set them all up the same. We'll replace y with y. We know our a value already. We're looking for b, and in this case, it's to the 1st power. So this one I'm simply just dividing 81 by 6. And when I do that, I get that my b is equal to a 13.5. So that one was easy because it was an x of 1. But this one, had an x of 6. But the step is replace y with y, leave your a value, we're looking for b, replace x with what x is, right? And we always use that second point for our x and y. I'll divide both sides by 5 here. And when we do that, we get 64 is equal to b to the 6th. We'll need to take both sides to the 1/6 power, which is also the same thing as the 6th root. And 64 to the 1/6 power tells us that our b is equal to 2. We can do this even when they are fractions. Same setup as always. Set up your y, leave your a value the same, set up your x. We're looking for b. When I divide both sides by 8 here, we'll get 27 over 64 is equal to b cubed. Now when I take the cube root on both sides, we will get 3 over 4 is equal to b. So I encourage you to pause the video and attempt this last one all on your own. I'm about to cover the answers, so push pause if you have not yet tried it. Replace the y with y. Leave your a value. Solving for our b value to the 4th power. There's nothing to divide, so I'm really just looking for b to the 4th. I'll raise up both sides to the 1/4 power. And when you do that, you'll get that b is equal to 5. All right. So that's how to write an exponential function that passes through 2 points when one of those points is the y-intercept. If you're level 5, you can stop the video here. We're going to move on for level 3s to solving the equations like we just did above, but with inequalities. And on these, the rules are the exact same. You need to get your bases equal before you can make any assumptions about the exponents. But what this is saying is that when we have the same base and same base, set your exponents equal, but keep your inequality. When you have same base and same base, set your exponents equal, but keep the inequality. So let's jump right down into some. So for us here, when we have 3x minus 4 is less than, I can re-express 1 over 27 as 3 to the negative 3rd power. Once we have that, we're going to set our exponents not equal anymore, but set up with the proper inequality. So in order for that original statement to be true, x must be greater than 1. And x must be less than 1. As long as I pick a value less than 1, you'll always make sure that this left-hand side is smaller than 1 over 27. And let's just pick a number that works for that. For a solution that could work as a test would be x is equal to 0, because 0 is less than 1. Let's try it. If I do 0, it's really 3 to the negative 4, which is 1 over 81. And 1 over 81 is smaller than 1 over 27, so it checks. You can always pick a number in your solution range to see if it checks out, and in this case, it does. So all this page is more examples of what we did previously. So re-expressing the 4, except the only change is that instead of setting your exponents equal, you will set them up with whatever the proper inequality was. But otherwise, the exact same process. So to finish this one off, I could add 4 to both sides. I could subtract that x, and then divide by 3. So I'll do one more here. We'll do one of the more challenging ones, number 8, because otherwise this works just like above, except we have to set them with the proper inequality rather than an equal sign. This one here is going to require you to know bases. You'd have to know that both 27 and 243 are powers of 3. 1 over 27 is 3 to the negative third power, because 3 cubes 27. 1 over 243 is 3 to the negative fifth power. And so you get better at those the more you work with powers. But once we have that, I would now just set up my inequality and my exponents. Now you might be wondering, Mr. Cottle, do we need to flip the inequality? We just multiplied, by a negative number right here, and also by a negative number here. All we do is rearrange the way things worked, so that's not actually going to count as needing to flip the inequality. The only time you flip the inequality is when you do, like if I was to say I'm going to divide both sides by a negative number or multiply both sides by a negative number. This is just re-expressing the way the problem looks. 3 to the negative third is the same as that, so it will not cause an inequality flip. So here I've got a negative 6x minus 3. It's less than or equal to negative 15x plus 10. I can add 15x to both sides, add 3 to both sides, and get that x has to be less than or equal to 13 over 9. And you'll get a lot of weird answers on these, but we'd expect one with the way that this problem initially started off with strange fractions. But otherwise, this skill is the exact same as the other page, except at the end, when it comes time to set up your inequalities, use the inequality sign instead of the equal sign.